Let's talk about the generalized power rule. Now, in Math 5A, first semester calculus, we learned about the power rule. And the power rule says when you differentiate a monomial x to the n, you bring down the power of n, and then you're going to subtract 1 from the exponent. So before, when we looked at this, this n right here had to be an integer. So what's different between this generic power rule we learned before and the generalized power rule is just one very small difference. The difference is that if n is any real number, we can write a power rule for that. And the key idea is that n is allowed to be any real number, not just an integer. So when we write down our generalized power rule, we get n times x to the n minus 1. So really, this power rule looks exactly the same as the power rule that we learned about in first semester calculus. The main difference is, as I said before, the exponents are allowed to be any real number. So let's take a look. When we look at this example here, uh, this time our power here is a pi. Pi is not an integer, it's a real number. So when we take the derivative of x to the pi power, you just bring down the pi and you could have x to the pi minus 1 because we have to subtract 1 from the exponent. Let's take a look at another example. If you had e times x to the e power, in this case, this e in front is a constant multiple. So if you wanted to, you could factor that constant multiple out first. So this could become e to the derivative of x to the e power. And then when we want to find the derivative of that, we have to use our generalized power rule. So this becomes e times, you bring down the e, and then you subtract 1 from the exponent. So it's e times x to the e minus 1, which we could simplify to e squared x to the e minus 1. Okay, so we have those two examples. Another thing that we could talk about is we could talk about this number e as a limit. Now, this is something that we actually use this when we talk about series. Series later. Okay, but this is probably a good time to introduce the idea, and we'll actually use it a little bit later on. So there's a couple of different limit definitions of E. The first one looks like this. We got quantity 1 plus x raised to the 1 over x power. That's one definition of E, and that's when x goes to 0. The other definition of E just kind of manipulates this situation. So instead of having x go to 0, we're going to have n go to infinity. So when n goes to infinity, you could rewrite that x going to 0 as just 1 over n, right? As n goes to infinity, 1 over n is going to go to 0. And we're going to replace the 1 over x with just an n. So we put an n power over here like this. Okay. Let's take a look at why this might be true. So let's start off with letting f of x be equal to the natural log of x. Then we know that when we take the derivative of f of x, that's going to give you 1 over x, right? Okay, so in particular, if I were to substitute a 1 in for x, then the derivative of f prime of 1 is just going to be 1 over 1, which is just 1. So on the one hand, we know that f prime of 1 is equal to 1. Now, let's use that knowledge, f prime of 1, but let's write it a different way. Let's use the definition of the derivative. The limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h. Let's simplify this and calculate what we get. So we can really replace the h with an x. And let's write this as the limit as x goes to 0 of f of 1 plus x minus f of 1 divided by x. Now we can substitute in, we know that our function f of x was natural log of x, so let's replace those f's with natural logs, and we get the limit as x goes to 0, natural log of 1 plus x minus natural log of 1 divided by x. Now we know natural log of 1 is equal to 0, so really this becomes the limit as x goes to 0 of natural log of 1 plus x divided by x. And finally, we can really use our third law of logarithms. So we get the limit as x goes to 0, 1 over x, natural log of 1 plus x. And we could use our third law of logarithms to take this part in front and to bring it up top to the exponent over here. So we're going to get this is equal to the limit as x goes to 0 of natural log of 1 plus x to the 1 over x power. Okay, so let's put this all together. On the one hand, we know that we started off with f prime of 1, and we already calculated that f prime of 1 is equal to 1, so I can write that this implies 1 is equal to, and then after doing all of our calculations over here, we ended up with this limit as x goes to 0, natural log of 1 plus x to the 1 over x. So let's write that on the right-hand side. The limit as x goes to 0, natural log of 1 plus x to the 1 over x. At this point, we're going to raise both sides by e. So putting all together, after raising both sides by e, on the left-hand side, we're just going to have e to the first power, which is e. And on the right-hand side, you're going to have the limit as x goes to 0. E to the natural log of something is just something, so we end up with 1 plus x to the 1 over x power. And that's what we were trying to prove. All right. So this basically describes how we can write e as a limit. All right, everybody, take care.